still on our section, which is to do with inverse trig functions and right angle triangles. And here are 4 questions, basically the same type of question, where we're trying to find the interaction between a trig function, sine, secant, whatever it is, and an inverse trig function like inverse sine or inverse cosine. And here are 4 examples, and yours will be similar but different numbers. So I'll start with the first one, question 2. We're being asked to find the exact value. So, I mean, I could just go into the calculator, right, and type this in, but if I did, I'd get, you know, nothing 0.1234. They don't want that. They want an exact value. So what you do is, is you start with the inside piece of information, which is that guy. And we know that's an angle whose cosine is equal to that. So I'm going to say theta. That's what I'm going to call that missing angle. So these give you angles. So theta is going to be that. If I then take the cosine of both sides, that information becomes the cosine of theta equals 8/17. And then you build a right angle triangle using this information. So I'll call this theta. Right, which trig identity or which trig ratio uses the cosine? What are the 2 guys?
The adjacent and the hypotenuse.
Okay. So on my right angle triangle, I'm going to name the adjacent and I'm going to name the hypotenuse. I don't care about the other one, so I'm not even going to write it down. And I know that the adjacent is going to be 8 and the hypotenuse right now is going to be 7, right? Once I've got them sorted out, I'll then put in my opposite. And I want to find the opposite. And we're going to use Pythagoras. So 8 squared is that, 17 squared, not very easy to do. So 289. So if you subtract 64 from both sides, you get 225. And the opposite is going to be the square root of 225. So far, so good. Now, once I have created this right angle triangle, including the missing third side, I can return to this question. Well, since I'm calling all of this theta.
The square root of 225 is 15, by the way.
How much is it?
15.
Wow, should have checked that. So we're going to call this guy theta. So the sine of this guy becomes the sine of theta. So all I need to do is find out who the sine of theta is. And that's going to be opposite over hypotenuse. And that is 15. So that's going to be 15 out of 17. And when you are dealing with these type of situations here, right, and you're creating a right angle triangle, do you notice that I don't need to worry too much about pluses and minuses, because since this is a right angle triangle, aren't everybody going to be positive, right? So there are not going to be any issues, at least in this question, in that format. So let's pick another one. Let's try this one. It's a bit harder. So we're going to find the exact value of the secant of the inverse sine be 24/25. So I'm going to call the inverse sine the angle theta, which my pen's going, which means that we now know what the sine of theta is. and that is opposite over hypotenuse. So at this point, I can now create my triangle. And I'm only interested right now in the opposite in hypotenuse. And I'm going to put a 24 here and a 25 here. And now I'll put in the missing third one. And Pythagoras will get me the answer. So that's going to be the adjacent squared. Oh, yeah, nobody's going to do that. At least I'm not going to do it in my head. 24 squared is 576 equals that guy. So the adjacent squared is going to be 100. Oh, not risk it. 576. Try that again. 625 take away 576. Oh, would you think it's actually a nice number? Now we want to find the secant of theta. Can anybody remember the secant of theta in terms of adjacent, hypotenuse, that kind of stuff?
Hypotenuse over adjacent.
Which is essentially the upside down cosine formula. Great. So what you've got here is 25 over 7, and you're done. Are you comfortable with how we tackle this type of question? Right. Now, they've got one weird one, which is 19. So as kind of the last situation, let's show you how that one works. We're being asked to find the exact value of the sine of the inverse tan of x. So I'm going to set it up the same way as I did everyone else that looked like this. I'm going to call this missing angle theta. And then I can convert it essentially by taking the tan of both sides to get that. And then I have to do a little trick. I need a fraction, and I only had x, so I'm going to call it x over 1. And now I can label this the opposite over the adjacent. And at this point, we build our triangle. And I'm only interested right now in the opposite and the adjacent. The opposite is x and the adjacent is 1. Now I'll go looking for the third side, which is hypotenuse. And the hypotenuse squared is 1 squared plus x squared. And so you take the square root of that. And no, that is not 1 plus x. I wish it was, but the square root of 1 plus x squared cannot be simplified, right? You can't do anything to make it nicer, right? When you have plus or minus inside the square root, that's the end of the road. You can't do anything. Right? So I now should be able to, get the answer to the particular one that they're asking us for. In this case, they want us to find the sine of this guy. So that becomes the sine of theta, which is opposite over hypotenuse, which in this case is x over the square root of 1 plus x squared. Are you comfortable with that? Right. Now, I'm going to take you over to some homework questions. Because I found out today that there's a little hiccup. Okay, are you looking at question 17 right now? Okay, right, so I'm going to go up to a different question. And right, These ones where you're going to use your calculator to find, say, inverse sines, inverse cosines. So the one I'm going to do is this one, the inverse tan of -9. No, let's do this one, the inverse cosine. That one's easier to do. So on my calculator, I'll make sure I'm in degrees, which I wasn't. So I'm now in degrees. And I'm doing the inverse cosine of -0.4. And the answer I get to, God in Himmel, to 5 decimal places is 113.5781. And the next digit is a 7, but the one after that is an 8, so we get 8. Okay. So the answer is 113. Oh, shooting spice and things that aren't nice. Can you see what I did wrong? My classic never reading the question. What's wrong?
It's supposed to be in radians, not degrees.
It's supposed to be in blinking radians. So that's not the question I was having issues with, but since I've started this one, I better finish it, right? So in this case, it's going to be a little bit more obvious. So you just do inverse cosine and -0.4, and you'll get an equally ugly but different answer. So it's going to be 1.9823, and then it's a 1.3, so 1. Now, where's the ones that are in degrees? Help me out here, Katie.
Those are the here, once again, I'll pull it up
Give
again.
me a question number with degrees, because that's the one I want to dwell on.
Okay, it's the like, oh, I'm pretty sure it's 10. No, I think it's like
Here we
12,
are.
14 or something.
Yeah, gotcha. Question 14.
14, okay.
Okay. So there is a minor hiccup in questions. Let's get the numbers right. Questions 14, 15, and 16. So let me show you what's going to happen there. Now that I've found the damn things. We're being asked to solve essentially a very simple equation. So in question 14, we're being asked to find this guy. And we're being asked to only find the answers between 0 to 180. So that's important. And in this case, don't you just find the inverse sine of 3/4? So I go to my calculator. I make sure that I'm in degrees, because they tell you they want the answer between 0 and 180. So that means they want the answer in degrees. So back to degrees again. And now I'm going to go inverse sine. And I'm going to do 3/4. Nothing special. And the answer is 48. And how many degrees do they want here? 1 decimal place. Okay. So 48.6 degrees. What possibly could go wrong, right, Kay? What? So you go to your box and you type in 48.6. And it will tell you you're wrong. And I'm about to do that. Now that I've got an answer. 48.6. And I'm going to submit answer. And it is wrong. And it's not really, really wrong. It's 48.6 degrees. Okay, you're on, Katie. Where do you find the degree symbol?
On the symbols button, right there.
Now watch.
Ding, ding, ding.
Hey,
Supposed to have more than 1/8.
Is it 131.4 as well in a comma separated this?
oh, there's two of them. Right. Thank you. Well, my question was wrong in the sense I didn't write down everybody. But it would have been wrong without that. So let me make another mistake. Comma separated list. Comma separated list. The degree. Oh, I hit it. There we go. Whew. So just a little idiosyncrasy. Now, there is a question, I remember seeing it, where they had a degree symbol already outside the box. Now, I bet money if I put 47.2 degrees inside that box, won't WebAssign also go and say I'm wrong? So why some questions, they give you the degree symbol, in which case you don't need to do it, and other questions where they don't give you the degree symbol, in which case you need it. I don't know why WebAssign's just been a pain in the butt there, but can you imagine that you might talk yourself out the right answer because you know, oh, I must be wrong, when really it's, oh, I needed a degree symbol and it wasn't clear. So I wish they would always just put the degree symbol outside or never do it, right? So that you're consistent.
Yeah. I ended up having to practice another version because I was like, it's not wrong. And then
Correct, it's not wrong.
I did the same thing. I didn't put the symbol in for the practice. And then I clicked on show answer to see how it wanted it written. And it was that, it was just the symbol different.
So then you notice.
Yeah.
But wouldn't it be very easy to look at it and not notice what you'd missed? Because you'd see it and you say, yeah, that's my answer. Well, in your head, it was your answer, but you physically hadn't written a degree symbol. So what can I say? WebAssign is a pain sometimes. You just have to live with it. It's software, right? If it was a human being, people would know what you were meaning. So to finish off this section, I want to do the two application questions, or at least versions of them. And then we can move on to our second and final section from this week. So in question 21, you've got a little puzzle and a 16-foot ladder is leaning against a building. So there's the ground, there's the building, that's 16 foot. We'll make the assumption that the building is vertical and the ground is horizontal. So can you see my right angle triangle? Now, if the base of the ladder is 7 feet from the building, so if that is 7 feet, what is the angle of elevation? Now, the angle of elevation means that angle there. So what they're asking is to find theta. Are you comfortable about that story, right? 16-foot ladder, 7 feet away from the base of the building. What is the angle of elevation becomes what is this angle? Now that I've set this question up, I won't take it all the way to the end, but I will do one extra step. What name do you give to the side called 7?
Adjacent.
And would you agree this is hypotenuse? So far, so good. Which one of the 6 trig ratios? Really, you only use 3 when you do right angled. So which one of the 3 trig ratios do you use in this combination?
Cosine.
Agreed. And won't you just hit inverse cosine and write 42.1 degrees or whatever it is? And question 22 has a different story. Here's the ground. An 88-foot tree. So here we go. Oh, pretty good artist. That's a tree, 88 feet tall. And it casts a shadow that's 150 feet long. So can you imagine the shadow? So from there to there, is 150 feet long. What is the angle of elevation of the sun? Is asking you to find that guy. Right. So, angle of elevation of the sun. What do you call 150? What's the name of that side?
The
Adjacent.
adjacent.
I was going to say adjacent, opposite thingy bob. What's 88 feet going to be, that one?
Opposite.
Which one of the three trig ratios do we use this time?
10.
10. And because this is a right angle triangle, you don't need to worry about the other angle or which quadrant it's in. None of them really matter, because in right angle triangles, aren't the answers always positive? Right? So, you know, the angle you're going to get is going to be in the first quadrant. And we are finished that section. Is there any questions before we move on? Okay, I'm going to let my dog in because she's going to rip my door off. Right, you be quiet, young lady. No. I'm busy. Go on. Play with your brother. She's learned to knock my hand so I can't use the mouse. I'm going to put you outside, young lady. I am. You listening? No. No. She is spoiled. It's my fault. Okay, the next section, if I can use my mouth pointer without her banging into me every 2 seconds, is going to be section 6.5. And a rule called the sine rule. SOHCAHTOA is used when you have right angle triangles, right? So if you want to find missing sides or missing angles in a right angle triangle, SOHCAHTOA is your go-to guy, right? But you know, there are lots of triangles that are not right angled. And don't you still want to find missing sides and missing angles in those guys? And for those non-right angled situations, right, triangles that are not right angled, they created the two rules. The one we're going to deal with right now for this week, and it's called the sine rule. Now there's another rule after that called the cosine rule. And basically they allow you to find missing sides and missing angles in any triangle you like. So that's pretty cool. So first thing I'm going to talk to you about is trying to deliberately not make these look right angled. But it's almost no matter what I do, I end up accidentally making something look right angled. So imagine that's just any old triangle, right? 80, 40, 50, right? That kind of any old triangle, right? If you call a triangle A, B, and C, so you name these points here, A, B, and C. The way that we name the sides, we don't have opposite adjacent hypotenuse, right? That doesn't work with non-right angle triangles. There's no way of telling which one's which. So what you do instead is you name the sides a little bit differently. This guy here is called angle B, but the side that's furthest away from it, if you like the word opposite, the side that's opposite is little b. And this is angle C. This guy here is angle C. And this is called little c. And this one here is angle A. And this is called little a. Are you comfortable about how you name the sides of a triangle? You name it according to the angles that you're given, right? So imagine I have this triangle. My triangle happens to be called, say, PQR this time, because very often they have different layers. So, what name do we give to this side here that my pen is pointing at?
A.
Say it again.
Little p.
Correct. And this side, whoops, this side down here.
R.
This is little r. And well, pretty obvious that that's little q. Are we comfortable now that if I gave you a triangle and I called it A, B, C, D, E, F, P, Q, R, whatever, that you'd be able to name the sides little a, little b, and little c? You're comfortable about what each side is called? And it all depends on what the capital letter angle is called. So far, so good? Right, now, let me write down the sine rule for you. It says that for any triangle you could possibly want or draw, any that exists, this triangle here. Oh, shooting space. I can never remember this. It's little a over capital sine A or capital sine A over little sine A. I know the Americans do it different from me. Darn it in space, which is it? Because I don't want to start doing it the British way, and then when you go to your next class, they'll laugh at you because it's upside down. By the way, both methods work, and it's just how you orientate them. Okay. I'm pretty sure it's sine A over sine A. Okay, so the sine rule says that the sine of angle A over little a is the sine of angle B over little b is the sine of angle C over little c. And that is the formula called the sine rule. So it's a little bit different than most formulas. Aren't most formulas one guy equals another guy, like those two guys, right? Wouldn't those two be considered a formula, right? This thing is equal to that thing. And we are going to be solving the sine rule based on a very similar kind of idea. So let's give you an example of how that might work out. Suppose I tell you that this angle here is 101 degrees. Oh, I have to have names. This is A, this is B, and this is C. So this is 101 degrees. Let's suppose I tell you that this angle here is 25 degrees. And I tell you that this fella up here is 15, maybe 15 years. And I want to know this guy here. So the question is, for this triangle, find the length of the side AB, right? So taking this nice and slow. First step, step one, is name all the sides. So in this case, little a, b, and c. So okay. The one that's called X, is its name little a, little b, or little c? Right, the side that's called X.
Little c.
A, little c. Okay, the one that's called 15, little a, little b. Who is? Okay. And so little bc. So not much S step, right? Name the sides, right? Give them the letters, in this case, little a, b, and c. Step 2. Find any missing angles a little caveat, if possible, because in half the questions, it's just not going to be possible. Now, this badly drawn thing is a triangle, right? So far, so good.
It appears
Now,
to be so.
it appears to be so badly drawn, but it's a triangle. Don't all triangles add up to 180? Whether they're right angled or not, all 3 angles in every triangle add up to 180. Can I find angle C?
It's 54 degrees.
Right, tell us where you got it from.
I just took 180 and subtracted 125.
Yeah. So if you take 180 and you take away the 2 guys that you know, you are left with, I forgot what that's going to be. Thank you. You're going to be left with 54 degrees. No particular reason for the color code. I'm just putting it in green because I want to, right? So step 2, if you can, in this case you can, fill in any missing angle. Now step 3, write down the sine rule. And, well, I call it tick. I don't know what Americans call it, check, whatever. And tick off the info you know or you want to find. So you write down the sine rule, which is this guy. And you tick off everybody you know. I know angle A, I know angle B, I know angle C. If I know an angle, I can find those guys. We agree they get checked off. I know A is 15, so I'll check that off. Aren't we trying to find X, which in this case is called little c? And so I'm going to check that off. When you do the sine rule, this is typically what you're going to see. You're going to see 2 pairs where everything is checked off. You see that guy in the middle? Ignore him. We are only, at any given moment in time, you only use 2 out of the 3. Does that make sense? If you're going to have an equation, you can't have 2 equals. I mean, you can't really deal with 2 equals, right? So in this case, step 4 is coming up. Use the 2 ratios, basically fractions, that are all ticked off. I think Americans call that checked. Should I call it checked from now on, now that the words come to me? Did you know what I meant when I say ticked off? Is it only because context and you've never heard it before? If I stick to checked, I don't care. I'll probably end up using both.
I normally say checked, but yeah, under the context, and I have heard it before, yeah.
Okay,
Tick
so
box.
it works. So whatever one of those 2 words I end up saying, because my brain will just throw in whatever word comes to it first. In this case, you got them ticked off. Can you see that the pair that we're talking about here are those 2? Does that make sense? Right. Now, as I say, this is really slow. I mean, once you get up to speed, you won't be writing down step 1, 2, 3, 4, right? You'll do it as part of a big process. So I'm now going to on to step 5. fill in all known values. So anything that is a number, you're going to fill it in. So in my case, I'm just rewriting it again because it kind of makes sense to do it this way. I know that angle A is 101, so it's going to be the sine of 101 degrees. And I know little a is 15, so that goes there. I know C is 54 degrees, so it's going to be the sine of 54 degrees. And over little c, now I could keep calling it little c, but just to make things weird, can I call it little x as well? Because isn't little x little c? At some point in time, I'm going to call it x anyway. So fill in all the known values. And solve. Okay. You are going to deal with a lot of questions that involve one fraction equals another fraction, right? That's very typical when you do the sine rule, right? Fraction equals fraction. Here is your clue. It's a visual clue. Watch what my fingers do. What are you going to do next?
Cross multiply.
And if you go those two, you get x times the sine of 101 degrees. And if you go this way, you get 15 times sine of 54 degrees. What do I do next?
Divide by sine of 101.
Does that seem logical? Does that kind of make sense to you? How we are solving this question? Make sense? Right. So at this point, it's really calculators because you're not going to get exact values for any of these. So 15 times the sine of 54. Uh-oh. Okay, I'm good. Make sure that I'm in degrees. So 15 times the sine of 54. I'm divided by the sine of 101. And let's say the question was to 1 decimal place. We now have 12.4. Let's say the units were meters. Do you like the flow of this question? Does each step kind of follow on to the next? It's not why on earth are you jumping from here to here. It does have a kind of flow to it. Because essentially, the sine rule, I know it has a formula, but isn't it again more of a process? It's you do this, then you do this. And if you stick to the process, right, trust the math, you're going to get an answer. It's going to work. So that's essentially how to use the sine rule to find a missing side. So let's do another one. But this time we're going to use it to find a missing angle, okay?
And then just to confirm, Pythagoras works on a non-90 degree angle or 90 degree or a right triangle.
Pythagoras is for right angle triangles, right?
Okay.
And this is for well, technically you could use it for a right angle triangle, but I wouldn't, right? This is for everybody else. So use the sine rule and the cosine rule for non-right angles and use, SOHCAHTOA for right angles. So think of them as two separate groups of questions. If it's right angled, SOHCAHTOA. If it's just a normal triangle, everybody else, sine rule, cosine rule.
Are the
All right.
sine
I
rule and
was just checking
cosine rule?
if Pythagoras was applicable here, but it is not.
No,
it.
it's not. No Pythagoras. Anthony, you were going to say something about
Are
cosine
the
rule?
sine rule and cosine rule the exact same, except one of them using sine, one of them using cosine?
Different formulas. One does use sines, this one, and the other one does use cosines, but the cosine rule formula is totally different. This is 3 fractions equal, that's the sine rule. Cosine rule is actually 2 formulas, one for an angle, one for a side, and quite different looking as well. So let's
Okay.
find a let's find a missing angle question. Come on. Okay, this is a version. And I've got a triangle. They don't have a lot of imagination, so most of the triangles are going to be called ABC. In this particular question, no, that's not question. No, I don't want question 4 because it's not really the question. Okay, I'll move it on to question 6. That's fair. Now, this side here is 11, and this side here is 11, and this angle up here is 64 degrees, and we are being asked to find this angle here, which I'm just going to call theta. Can I change this question a little bit? It's not that that won't work. It's just because these numbers are the same, you might pick up bad habits and think that certain things are true when they're not. So I'm going to do a little tweak on this. If that's 11, that's 64. I hope I haven't screwed up the question. I'm just going to make that 14, right? Just so these numbers are different. Because really, in excuse me, in the vast majority of questions, aren't triangles sides going to be different? Yeah, it's more likely than not. So here is our guy. Step 1 is name all the sides. Well, that's little c, that's little b, and that's little a. You comfortable with that, right? Little a, little b, little c. So far, so good. Step 2 would be find any missing angles if possible. Would you agree right now, I can't find any other angles, right? There's just not enough information. So step 2 was a dud, right? Couldn't do anything. Now we move on to step 3. And in step 3, we are going to write down the sine rule. And we are going to check off everybody that we know or are trying to find. Well, I know little b, check him off. I know little c, check him off. I know angle C, check him off, and I want to find this angle, so I check this off. Are you comfortable about the 4 guys that have little tick marks on, right? Little checks. So step 4 would be use the 2 ratios where everything is checked off. So step 4 can go here. So I'm going to take the sine b over little b is equal to the sine c over little c. And now I'm going to move on to step 5, which is fill in all the known values and solve. Well, I want to find that guy, and I'm going to call him theta now. And over 11, and it's going to be the sine of 64 over 14. Are you comfortable with what we did here? And there's my little visual clue again. Come on, don't get cross. What's the answer? What do I do next?
Cross multiply.
I even put in a clue there, don't get cross, and nobody caught it. Did you catch it, Tony? You did, okay. What do we do next?
Divide
by
both sides
14.
by 14.
Agreed. So I'll go here and I'll do 11 times the sine of 64 divided by 14, and I'll get that guy. And I just thought of something that can save me one line of working. What should I do to both sides to find the missing angle theta?
Multiply everything by the inverse sign.
Not so much multiply by the inverse sign, but I know what you mean. You take the inverse sign of both sides. I know that's maybe being fussy in the words, but that's not really a multiplication that we're doing here, isn't it? Finding the inverse sign of something. So back to my calculator. I can do the whole thing in one go then. So it's 11 times, that mess says sine of 64, all divided by 14. And to one decimal place, the missing angle is 44.9 degrees. So that guy in there is 44.9 degrees, right? Now that I know that this angle is 44.9, can I find angle A? Great. I now know that this is 44.9. I can now find angle A. What would be the calculation to find angle A?
180 minus 64 minus 44.9.
So that's 108.9. So 108 gives me 71.1 degrees. So I now know 71.1 degrees. Well, now I know all the angles and I know two of the sides. Shouldn't I be able to get the last piece of the puzzle, which is the side called little a? Great. Now, that would be the sine rule, except when I tick off everything I know, we get that. Oops, wrong one. We get that. And everything that I want to find, we get that. Do you see when you're finding the last piece, you now have everybody checked off. But you can only pick two, right? You have to have somebody equal somebody. Now I'm keeping this one because I want to find A, right? So it's pretty obvious I need this one. Could I do A and B? Would that be okay to use that pairing? Yeah. Could I use A and C? Sure. Would it make any difference? No. As long as you're accurate about rounding off. And whoops, I think that is a perfect time for us to finish. So last name and bye-bye for now. There's some more information about the midterm that's now online. So if you want to look at it sometime today, that's great. Tomorrow, I'll spend some time talking about it and then we'll move on and do some more of the sine rule.